Okay, so first thing I want to say is this. First, F21 curves the path toward M1. And, yeah, put quotes around that because toward might be a little ambiguous, but I think you get the idea. And the vector, the analysis of the vectors tells us exactly what that means. Okay, if the centripetal acceleration, and I said centripetal acceleration, didn't I? Okay, if a centripetal force equals F21, and since this thing is curving, there is a centripetal force times the center of whatever osculating circle it happens to be on, and we don't necessarily understand that terminology. People who are doing our multivariable calculus do. Anyhow, the path is going to be a circle. The condition is that the centripetal force of the curved path equal the magnitude of the force attracting this mass to this mass, attracting the satellite to the planet, for example. Well, that condition leads us to say that you have a circular orbit if and only if F21 equals centripetal force, which is m2 v squared over r, because of course centripetal acceleration is v squared over r. Multiply that by the mass m2, you get the force on m2. So the gravitational force under these conditions, if your velocity is just right, supplies the centripetal force necessary to keep the object moving in the circle. It follows then that we have a circular orbit of m2 around m1. Again, in the case where m1 is much, much greater than m2, we've got a circular orbit of m2 around m1, provided the F21, the gravitational force, g m1 m2 over r squared, is equal in magnitude to the centripetal force, m2 v squared over r. Okay, well, that means that if you want to specify r, you can calculate the velocity. If you know what the radius of the orbit should be, you can get the velocity very easily, and it's very easy to solve this equation, and we get this. Now, when you take, you do end up with a v squared equals something, then usually your solution should be v equals plus or minus the square root. But since v is the magnitude of the velocity, you're not going to have the minus. Okay? So here's a condition. Okay? And if you want to say, okay, well, what's the radius of the orbit that'll match the velocity that I want? You probably wouldn't say that, but you might. And you can, of course, solve this equation for r, or this equation, equally easily, and find out what radius would go with a given velocity.